Exercise 6.3, question 10. What I've done to begin with is just to have a quick look at how this type of loci actually works. So I've rewritten the problem, as you'll see, just using the properties of the arguments of complex numbers. Now in fact, if we've got the argument of z minus a minus the argument of z minus b equal to theta, then what we'll get is the arc of a circle, and we'll just look at that to begin with. Okay, so this really is sort of year 10 circle theorems, but I've set up the situation and I've called the argument of z minus a the angle alpha, and the argument of z minus b will be this angle beta. And if we just use z angles, then what we'll notice is the large angle I've marked at the top will also be alpha, the angle as shown will be beta, and where I've marked alpha minus beta is equal to theta will be the argument of z minus a minus the argument of z minus b. So that's our angle theta there, and the circle theorems part comes in because what we should know is if we move the point z around on this circle, then the angle will remain the same as theta. In other words, this purple line will be the loci that we require, and I've just shown on the diagram it wouldn't matter which point of z we chose on there, the angle would always be theta. One thing to notice, because theta, if theta is an acute angle, then we'd want the major arc. If theta was an obtuse angle, it'd be the minor arc that we'd be interested in. So the quick method to draw this type of loci down is to first of all plot where the point A is. Secondly, to plot where the point B is. You must decide whether you want a major or minor arc, and that will determine how you actually draw the circle passing through those 2 points. And then you start from A and you draw the arc anti-clockwise ending at B, where essentially A is the point from the numerator of the original problem, and B is the point from the denominator. Okay, so this time we're asked to look at a region. So the question is slightly different. The things that I notice are, first of all, the 3 pi upon 5 is obtuse, so that'll be a minor arc we're interested in. And this time the upper boundary, if you will, is pi. And that's perhaps a little tricky to deal with, and it'll actually be a straight line, but I'll discuss that as I get into the problem. Okay, so first of all, I'll locate where the points A and B are. A is at 4 plus 0i, B is at 1 plus 0i, and I've drawn a circle through just because I know that it's an arc that I require, and furthermore, because the angle was obtuse, I know I want the minor arc, and in a second I'm going to draw in from A to B going anti-clockwise to give us the minor arc we desire. I'll draw in a pair of axes as well on the Argand diagram. Okay, now that's actually going to be the answer that we require in this problem, and that's really all there is to it, but let's have a look at why. First of all, if I make an angle on the upper boundary as shown, then it should be fairly obvious just by looking at it. The angle I have is an obtuse angle, and if I was to move that point around, then it would always be 3 pi upon 5. If I choose a point in between, then it should be fairly obvious that as you can see in the diagram, the angle, this time I've called it k, will be greater than 3 pi upon 5, and it will certainly be less than pi radians. And furthermore, if I choose a point on the line segment AB, then it should be fairly obvious that I actually have pi radians there. So that gives us this as the desired loci. Part B. Okay, well, I've written it out, and you'll notice that I've rewritten the arg part just so that it's in the correct format. I'm kind of thinking of vectors when I do problems like this. And again, I note that there's an acute angle here, so that's going to be a major arc, and I also notice that the angle at the centre would actually be pi over 2 radians. And for pi over 2, it's a right angle. Now that means that the angle at the centre is pi, and that tells me in fact it's going to be on the diameter of a circle if you think about circle theorems again. So this time I'm going to draw down the 2 points, 3 plus I and 3 minus I, and I start off with having a look at just drawing in this semicircular arc between them. And so for the arc I've drawn there, 3 minus I and 3 plus I would actually form a diameter. And as you can see, that would give me an angle here of 90 degrees. Now, I'm going to draw in a second arc as shown. It's a major arc, as I sort of discussed previously, and again I've shown that the arc here would be, and it looks to be about pi over 4 radians, so everything seems to be good. And I'm interested in all points that would essentially fall in between the purple and the green line. In essence here, what we actually have is a family, an infinite number of arcs in between 3 plus I and 3 minus I, all of different circles. And so what we actually want this time is the region as shown here. And if you were to draw a test point in there, and again draw the line segments into that test point from 3 plus I and 3 minus I, then what you would observe is that the angle made would be between pi over 4 and indeed pi over 2. And that's all there is to it. So there's our desired region this time.